All right, so today what we are going to do, since we've seen that in dimension one, it was useful uh, to, to, to compute and to have the eigenvalues of the second derivative in space. And now we are considering higher dimensions. And so in particular, we start with 2D domain. So we start with the following exercise. It is to try to find out what are the eigenfunctions of the minus Laplacian operator with Neumann boundary conditions. And so we work on the L2 space. Okay, you can start with A equals 1, and then we will see what happens when A is positive. Okay, so let's focus on this particular exercise where omega is the square of we start with A equals 1, so it's the unit square. And then we will see in the second part and next time how this generalizes to any bounded domain. So the problem is that we look for functions phi which verify minus Laplacian phi equals lambda phi on the square. So my domain here is the square. So as I said, we start with A equals 1. With the Neumann boundary condition, meaning that the gradient of phi, when I took the product scalar with the normal, must be 0 on the boundary of omega. All right, so if you remember, we have that cos k px satisfied k square pi square. So what are a good candidates for our problem? Let's try this. Let's try something like that. And so we'd like also that the integral over omega of after that but we'll see that after. Okay, so if I look at so minus Laplacian of such of phi xy, and here there's no reason to choose the same k. Let's put the L. So if I do that, if I apply minus Laplacian to phi, well, what do I get? I get minus Laplacian of phi xy equals k square phi square plus L square phi square phi. So, and I should write it KL and KL. So those are eigenfunctions of, sorry, I forgot, of course. Yeah, no, that's okay. Are eigenfunctions of minus Laplacian. So what we need to do is first, let's see if they satisfy the boundary condition. So do I have that the gradient of phi k L at point xy equals 0 for in the boundary. So the boundary is here, what's in red. So let's have a look at that. So if I take the partial derivative with respect to x of phi k L, what I get is sine k by x cos L by x, and I need to multiply it by minus k pi. If I take the derivative with respect to y, I got the same thing, but it's so it's y here, sorry. It will be the same kind of stuff, but L pi cos k by x sine L by x. So what happened when I take the scalar product with the normal? Assuming we start here with this part of the domain. So here you have that y equals 0. So on for x, y, so let's call this CG. Let's say AB. So this implies that y equals 0, so x belongs to 0, 1. So I look at since so here the external normal derivative is a vector with, so here in this part you have that the normal is 0 minus 1. Okay, so I don't need this because I have to multiply by 0, and I get minus L by cos k by x sine L by y, but this is 0. So this is 0. So this is 0. I can do that for all sides of the square, and my function, that's right. So I only did the thing for AB, but we can do the same thing for all the sides of the square, and I got that. That's right, equals 0 on omega. Now, what we want to have is also that we'd like to prove that phi chi L, phi k prime L prime dx dy equals delta, it's KL, k prime L prime, meaning that this is 1 if KL equals k prime L prime, and 0 otherwise. Okay, maybe I will need to put some constant in front here. We'll see. So we'll see, but let's start. So I'm computing the integral between 0 and 1, 0 and 1 of cos k pi x cos L pi y times cos k prime px cos L prime py dx dy. As you see, I can separate these things, so I get integral between 0 and 1 of cos k pi x cos k prime pi x times 0 and 1 integral cos L pi x cos L prime pi y dy, and here I forgot the dx. So I fall in the same case as the dimension 1. So I know that, in fact, this is, I remember, for example, there's many techniques to do this computation. It's elementary for you because you're graduate students, but you just apply that cos of a plus b equals cos a cos b plus minus, sorry, sine a sine b, and you have cos a minus b. So here you got a plus, and so if you sum up these two, you get 2 cos a cos b, and we did that last time. So I know that this is 1. No, this is 0 if k is not equal to k prime, and when k equals k prime, this will be 1/2. All right. So in fact, I need to put here. So at the end of the day, if you assume that phi k L equals square root of 2 cos k px cos L py, and just so you need that phi OO equals 1. uh, and that's it. And the other one is that. Then you have that the integral between the integral over omega of phi k l phi k prime l prime equals what we want. 1 if k l equals k prime l prime, 0 otherwise. So we're good. So this is Hilbertian basis. We will see why the next time. And I have all the eigenfunctions and eigenvalues. So to summarize, my eigenfunctions are KL equals pi square L square plus K square. And so my eigenfunctions are 1 if K equals L equals 0 and square root of 2 cos K pi x L y otherwise. Okay, so one thing that we can remark is that you can see that, so my first eigenvalue is 0 because Laplacian of 1 equals 0. So lambda 0, 0 is 0. And then you have that it's you could find you can order your eigenvalues. For example, I will put here lambda 0 1 equals lambda 1 0 is less than lambda 2 so actually so 1 is less than lambda 2 0 equals lambda 0 2, etc., etc. So you can you can order all your eigenvalues, and you have that limits as KL goes to infinity of lambda KL is plus infinity. All right, so those are things that we are going to study in the generalized way in the next session. So what happens if omega, so we replace A 1 by A. So in this case, in order for things to work, we have to consider phi KL equals so for example 0 A of 1 equals A square. So for the first eigenfunctions, if you want that to be 1, you need to take right? So equals Otherwise, you can choose the same, but you have here to divide by A. The thing is that you need the boundary condition. So yeah, you need that to be a multiple of k pi. So if you choose your function like that, it's good. And yeah, it doesn't change here. Okay, but now what are the eigenvalues? So lambda KL, if KL is not 0, 0, will be K square pi square divided by A square plus L square pi square divided by I square. So that what I wanted to emphasize is that you can see here that the eigenvalues are inversely proportional with the size of the domain. Okay, that's a result here. We went from a size of A for the side of the square to of side of 1 to a size of A, and the eigenvalues decrease accordingly because you have the A square here on the denominator. So the eigenvalues of minus Laplacian are inversely proportional to the area of So next time we will consider the equation minus Laplacian phi equals lambda phi for omega subset of R and a bounded domain.